took a Yapsy talk and compressed it down to what I hope is about 5 minutes, and we'll see if we can make it work. Nathaniel, Noel, do you kids know where this is?
Yeah.
Where?
Philippines.
Okay, how's the traffic there?
Bad.
Okay,
Very bad.
there we go.
Yeah,
Okay.
Very bad, and you don't even need to wear your seatbelt.
That's true, yeah, because you can't move very fast. Okay, this is a few minutes of flocking. How hard things should be possible or minimally painful. A lot of people, their first experience with file locking is things like this, little pop-up error messages telling them they can't do what they want to do. But locking is, we have it to solve difficult problems. And the problem that we try to solve with flocking or locking is the problem of race conditions. So a race condition is multiple competitors for the same prize or the same file or the same resource. Why are race conditions a problem? In eternity, there's no time, only an instance long enough for a joke. Well, between every operation in concurrent programming, between every operation, there's an eternity of time, right? And so an instant can be an eternity, during which time you can encounter file corruption, resources can disappear or be rewritten, ownership or permissions can change, context can change, the universe can change, and all bets are off. So it's really anybody's guess what can happen when you have multiple things competing for the same resource. We prefer deterministic outcomes. And so we have to assume that there's an eternity of bad jokes between each line of code. So that brings us to Perl's flock. To use flock, here's an example of we're going to open a file for input, and then we're going to obtain a shared lock sh, on that file because we're opening it for input. We use the fcntl module. We import the flock keywords such as lock sh. And this will open the file, and then it will lock the file so that nobody else can write to it. Or nobody else can get an exclusive lock against the file. They can only also get shared locks on the file. And so our goal is to narrow down eternity into a virtual atomic unit. Dalton's atomic theory was that a bunch of yada, yada, yada stuff, and then atoms cannot be subdivided, created, or destroyed. And we're going to skip past the part of atomic bombs and all that, or splitting the atoms, but we need a way to turn multiple lines of code into an atomic operation or to spend eternity for just a moment. File locking is like a traffic light. Only one direction has a green light at the same time. Only one process can have an exclusive lock at a time. So the F-control module, as I mentioned, provides constants for flock. And then on the right over here, there's a couple different types of locks we can get. First, we have a lock EX, which is an exclusive lock. And I'm showing that in the first instance, we're going to get an exclusive lock, and if we can't get the lock, we're going to sit around forever, essentially. Yeah, we're going to flock, or we're going to wait forever. Thanks. The second example is a non-blocking example. We're going to try for the exclusive lock, but we've also mixed in the lock NB, which means non-blocking. If we don't immediately get the lock, then lock just returns. And it returns a false value. So we can say, if we get the lock, then we do something, and if we don't get it, we do something else. So here's an example of using lock, of getting an exclusive lock on a file that we can write to. So this is a file being opened in read-write mode. We can read and modify the data there, and then at the end we can unlock and release the lock. And so we've achieved an atomic operation, essentially. Here we've achieved an atomic operation of, we've got the file open and we've locked it, and now everything we do until we unlock it is, from the perspective of everybody else, kind of an atomic operation. The lock modes are exclusive, shared, non-blocking, and unlock to release the lock. You can mix them together, so you can mix non-blocking into EX or SH using the bitwise OR operator. So here's some examples. Exclusive lock blocking exclusive lock on the top left, exclusive lock non-blocking on the lower left, shared lock blocking on the top right, and shared lock and unlocking on the bottom right there. You would use shared for file reads typically, and you'd use exclusive for writes. You probably don't need to unlock a file handle, and the reason is that it can be error prone. Someone could still be using the handle mistakenly after you unlock it. In reality, the old Perls, in really old Perls, the output buffer doesn't get flushed when you unlock a file, and so what could end up happening is you unlock it, and then somebody else writes to it before you close the file, and then when you close it, the output buffer gets flushed, and now you've got file corruption. Nowadays, and even in the old days, closing a file handle automatically flushes and unlocks, so you might as well just close and not call unlock, because mistakes can lead to a garbled file. Yeah. Now here's the problem. Locks are advisory. What does that mean? Over here on the left, we have somebody who's getting an exclusive lock, but on the right, we have somebody that's opening a file for append and just indiscriminately writing to the file. The person on the right, because they're never checking for a lock, has no idea that the file's been locked. Operating system level locking is purely advisory. So if not everybody is playing by the same rules, then you still have problems. You still have problems. So always check the return value of flock. Here we're going to die. Why would you get a situation where you can, where you would get a false value on a blocking lock? Well, somebody may have deleted the file and it doesn't even exist when you try to get a lock against it, and so that's going to cause flock to return a false value and not block. So moving along, open modes are tricky. So here we're trying a open for output, and then we obtain a lock. What's the problem here? Anybody know?
There could be somebody who does something before between opening and lock.
Yeah, well, that's one problem. Another problem is that when we open the file there for output, we are in clobber mode. And so we could be clobbering the file before we are certain that we are the ones that can own the file, before we can get the lock on it. So open for output. Mark Jason Dominus, in his talk about file locking, says that it's like taking a dump on someone's doorstep and then ringing the bell and asking for toilet paper. So anyway, so maybe we could try this again instead. If the file exists, then open it for append, or else open it for, well, that still is a race condition. There's a race condition between does it exist and did we open it and get a lock. So that doesn't work. Here's another one. Should we open it for input plus write? So this is not going to clobber the file. It's a great solution if you know the file exists. But if the file doesn't previously exist, then you're going to get or die, because you're opening for input. And if you try to open a file for input that doesn't exist, you get a false return value on open. So this only works if the file previously exists. Here's another problem. Until we have a lock, the file can still change. So if we open a file for whatever reason, and then we want to position ourselves at the end of the file or at the beginning of the file, we need to seek once we've got the lock, because somebody else could have written to the file, and so we don't know the file's length until we have a lock on it. So this is especially important if you're opening for append mode. What else? Semaphore files. If you want to open a file for output and you don't want to clobber, you can use a semaphore. You can open your semaphore file for output, get a lock on it, and then open your real file for output, and you don't even need to get a lock on your real file. As long as everybody's looking at your semaphore file, they can determine whether or not you have a lock, and you don't have to worry about clobbering. But there's a problem with that, and that is that not everybody is going to be looking at your semaphore file. So I think the point to all this is that every approach has its own upsides and downsides. Another one is to use temp files. Temp files are great because you can open up a file with a random unpredictable file name. It's all yours, nobody else can be using it. Do all of your file writing to it, and at the very end, rename that file over the original file after you've first obtained a lock on the original file. Sometimes you can avoid the locking issue by using temp files because the rename itself is atomic. But rename still falls down when you're working across file systems because you can't rename a file across multiple file systems. Okay, here's another problem we want to solve. Run only one instance, or the Highlander problem. There can only be one, you want only one instance of your process running. For example, you have a long running cron that can only run once an hour and must never run if another instance of itself is still running. So a trick from MJD's talk on file locking is to lock $0, which is your script's name, essentially, your program's name. If you can get a lock on $0, then certainly nobody else can be running the same script. And so then there's an even cooler trick. The way that he does is he locks the data file handle. And then you don't even need to know what $0 is. If you lock the data handle, then you're locking, again, your own personal script. Nobody else can be running the same script because you've gotten a lock on your data handle. And believe it or not, it works. So,
Isn't that an instance of data?
what?
Isn't that an instance of data?
No, it's actually the data of your file. So, yeah. So, what else should we worry about? New locks on the same file handle are okay. Why is this a problem? Imagine you get a lock on a file, and then or imagine you open a file and then you fork, and then one child gets a lock on it and another child gets a lock on it. Well, they both share the same file descriptor. The operating system is perfectly okay with you obtaining a lock multiple times on the same file descriptor. And so your two children can both get a lock on the same file descriptor or on the same file handle. This becomes a big problem with database handles. If you happen to obtain a database handle and then fork, then each instance that shares the same database handle has the potential of clobbering the database in a race condition. And this was a problem that came up a few days ago. I found, it's not work related, but I found where SQLite uses operating system level locks to lock the database. And so if you obtain a DBI database handle and then fork, then you've got a problem. So, yeah, so the takeaways: don't ignore locking. Semaphores can be useful. Locks are advisory. They're only useful if people actually look at them. Use atomic operations. You can use locks to create atomic operations, and avoid the issue with temp files. There's an eternity between each line of code filled with bad jokes, and I think that's it. So, thanks.